Okay, in this video, we're going to begin section 2.3, and we're going to focus on calculating limits using the limit laws. Okay, and I'm going to go over the limit laws worksheet here. This is attached in your notes. So on this sheet, I've got some basic limit laws and then some other limit laws, including some things with trig functions there. In this first law here is basically saying the limit of a constant is always the constant. Okay, so you can remove the limit notation there if you just have a constant inside the limit. Anytime you're working with a power function, you can make a direct substitution for whatever number a happens to be. Okay, over here you'd have a power of 1, right? So you can make a direct substitution there with the a value. And of course, when you make a direct substitution, be sure to remove the limit notation, okay? You've now calculated the limit. Now, in law 4, you would assume that a is in the domain of the function. So, like if you have an even index here, a has to be a positive, okay? Like you're not going to take square root of a negative. That's not a real number, right? Here's some other limit laws to know. In this first one, we're basically saying that constants can come out of limits. And in the second one, we're saying that the limit of a sum is the sum of the limits. Okay, if you have a single limit and you're adding two expressions, you can split that into two limits. Same thing with subtraction, multiplication, and division. Okay, the limit of a difference is the difference in the limits. You can split that into two. The limit of a product is the product of the limits. You can split that into two limits. And the limit of a quotient is the quotient of the limits, provided that the limit of the denominator is not 0. Okay, we'll talk more about that here. So if you have a single limit, you can split that into several limits, that are either, add, subtract, multiply, or divide. If you have the limit of a function to a power, that's the same as the limit of a function to the power. Same deal with nth roots. Okay, the limit of the nth root of a function is the same as the nth root of the limit of the function. Again, you'll have to assume that you'll have something that's in the domain, like you can't take square root of a negative or something like that. Okay, we're not doing anything with I or imaginary numbers. As far as the trig functions, you can make a direct substitution if a is in the domain of the function. Okay, and of course drop the limit notation whenever you directly substitute in a number. All right, so having said that, I want to get some practice evaluating limits, and I'll be showing all the steps here in these at the moment. So let's take a look at my first example. The limit as x approaches 3 of 2x squared minus 3x plus 4. Okay, I can use my limit laws here. I know the limit of a sum is the sum of the limits. Limit of a difference is the difference in the limits. So I can begin by splitting this into three limits. And I know constants can come out of limits. Okay, so here's 2 is a constant. I can pull that in front. 3 is a constant. I can pull that in front. Now, I can use my limit law that says that if I have a power function here, I can make a direct substitution. That's this law here. Okay, so I can directly substitute in 3 into these first two terms. Of course, remove the limit notation when you do that. And then with the last term, the limit of a constant is always the constant. So I'm going to have 4 there for the last term. Again, make sure that you remove the limit notation. Okay, so then I have to just simplify this. 3 squared is 9, times 2 is 18, minus 9 is 9, plus 4 is 13. 13 would be my answer. Okay, here's another one. The limit as x approaches negative 2 of x cubed plus 2x squared minus 1 all over 5 minus 3x. Well, the limit of a quotient is the quotient of the limit, so I can go ahead and split this into two limits. And then the limit of a sum is the sum of the limits. Limit of a difference is the difference in the limits. I can go ahead and split this part here into 5 limits. And then I can make a direct substitute. Well, actually, I can also pull out the constants there, right? I've done that on these terms. And then I can make a direct substitution, okay, of -2 into each one of these terms here. Now, with this last term up top and the first term down under, we're working with limit of a constant is always the constant, right? So all I need to do with those terms is just simply remove the limit notation. And here's what the next line is. Okay, now I can simplify. So -2 cubed is -8. Adding 8, so that'd be 0. Minus 1 is -1. 5 plus 6 is 11. -1 over 11 would be my answer. Okay, and of course make sure that the answers are in exact form. Okay. Here's another example. The limit as x approaches pi over 3 of 5x times cosine x. Well, I've got a product. I'm multiplying, so the limit of a product is the product of the limits. I can split this into two limits. I can also pull the 5 out front of the first one. And now I can directly substitute in my a value. Okay, I'm going to have 5 times pi over 3. Be sure to drop the limit notation there. And then on the second term, I can just plug in pi over 3 and again drop the limit notation. Now cosine pi over 3, of course I'd want to simplify that. The adjacent side would be 1, the hypotenuse would be 2, so 1/2 would be the value of cosine of pi over 3. 5 times pi times 1, pi over 3 times 1/2 would be 5 pi over 6, and again you'll want to leave that in exact form. Okay, a couple things to mention here. The first thing is I want to mention the difference between evaluating a limit and estimating a limit. In the previous videos, when we were doing things with limits in a table, we were estimating a limit. Okay, now I've mentioned several times in those videos that a table is a poor option. Okay, I don't want to be guessing my answers. I want to know for sure what the answer is. The limit laws allow me to know for sure what the answer is. Okay, so at this point, unless you're told otherwise, I want you to break the habit of using a table. Okay, there's going to be very few times where we will ever do things with tables again going forward with limits. Okay, so consider that. All right, when they're asking you to evaluate a limit, they are not asking you to make a table. If you make a table on the assignments that we have, and I'm asking you to evaluate a limit, you're not going to get points then that you need because you didn't follow the directions. Okay, so again, only make a table if they are asking you to make a table. Again, make sure that your answers are in exact form here. Okay. Another thing to mention here is the notation. Now that's in all capitals. Okay, use this properly. I will be picky about this. Okay. I don't know, I guess I'm just weird. I want you to write correct mathematics, okay? English teachers are weird too. They want you to write correct punctuation, right? But it matters, you know? It matters what we're writing down, okay? Like if I'm trying to show somebody how to calculate the square root of 9, and I don't write the radical there, I just say the square root of 9 is 3. Okay, well, yeah, that's true. The square root of 9 is 3, but it doesn't look like I know what I'm talking about if I say that 9 equals 3, okay? The notation matters. It needs to be there, right? Otherwise, it's misleading then. Same deal here. So just to mention a couple of things that I'm looking for, errors that I've seen in the past, you know, from students make that you want to be careful with. Notice how on each and every step, I've got the limit notation included. Be sure that you're writing that, okay? Make sure that you're writing limit as x approaches 3, limit as x approaches -2, or whatever it is. If you don't write that, I will take points off, okay? Because the limit of a function is not equal to an expression, right? You can't remove the limit notation until you've calculated the limit, all right? So at this point here is when I'm going to calculate the limit. I'm going to go ahead and directly substitute in my number, and at this point I want to drop the limit notation, okay? I will see students sometimes continue to write limit as x approaches 3, and they've already plugged in their numbers. Don't do that. You will lose points. Okay, that's bad notation. You're not saying something that is correct there. Okay, so be sure that you drop the limit notation when you actually substitute in that a value, whatever it is. Don't just write, I'll see this sometimes, okay, where a student will write limit as x approaches 3, and then there's nothing in there, and then they say equals 13. I will take points off for that, okay? Limit of what? We always calculate the limit of a function, okay? You got to make sure that the function is inside the limit. If you don't write that, then it makes it look like the limit of anything, doesn't matter what we use, the limit of anything as x approaches 3 is always going to be 13. No, it's not. It's just like this problem here. If I say the square root of 9 is 3, but I don't actually write the 9, well, that's very confusing, right, for somebody. I don't think that this person is going to, this person is probably going to have some problems later if they're not understanding the notation. Same deal here, okay? The notation is extremely important. Make sure that you're using that correctly. Of course, make sure that you're writing x approaches 3, okay? Like I'll have some students just write limit. Limit of what? This is not the topic that you'd want to stray off and do your own thing, okay? You want to make sure that you are paying attention to the notation and using it correctly, right? You don't want to lose points on the assignments for bad notational errors. All right, now you'll notice that another thing about like these problems here, so it looks like all I've really done on these examples is I've just plugged the a value into the function, right? Like if I just plug 3 into this expression here, I get 13. If I just plug -2 into this expression here, I get -1 over 11. If I just plug pi over 3 into this expression, I get 5 pi over 6. Yeah, I agree. That's all we're doing, okay? Now this is the behind the scenes stuff using our limit laws, okay? So I sometimes get the question, do I have to write all this out if all I'm doing is plugging in the number into the function? No, you don't need to write all this out, okay? In fact, I would encourage you to just plug in the number because that's all we are doing. In fact, in general, if a is in the domain of f, then the limit as x approaches a of f of x equals f of a. You can directly substitute in that number and go right to the answer. I would encourage you to do that, okay? Now, the only reason why I'm writing out all my work here is just to emphasize the limit laws and the notational stuff. Whatever work you're showing, make sure that your notation looks good and that you're using it correctly, okay? Functions with a direct substitution allowed are called continuous at A, and we're going to study those later once we get into section 2.5, okay? So more on that topic later. But not all limits can be evaluated by a direct substitution, though. Okay, I mean, these problems that I was showing you up here, these are easy, right? Because all you're doing is you're just plugging the number into the expression. And an algebra student could do that, right? That's all we're doing. But more times than not, most of the time, we're not going to be able to directly substitute in that a value. Okay, so let's take a look at some more examples here. Let's go back to the tangent line problem. Okay, now remember that, so that was the very first problem that I had shown you in this chapter. We wanted to find the equation of a tangent line to the graph of y equal x squared at the point 1, 1. Now the way that we did that is by selecting another point on the parabola, which I was calling point Q. Point Q was very close to point P, and point Q had coordinates x squared. And by working with 2 points, P and Q, that allowed me to create this formula for the slope of the line passing through those points. I was calling that m sub PQ. Okay, and if you were to look back in the notes, you would see that for that problem, m sub PQ was x squared minus 1 over x minus 1. Okay, now we had used a table in that problem because that was the only thing that we were knowing at that point. Okay, but let's look at that problem again. Now, previously we had guessed that the slope of the tangent line is 2. Okay, based on what we had seen in the table there. Okay, now if I were to calculate this limit directly, now having known my limit laws, here's what's going on. So the numerator is going to factor, and that's going to allow me to cancel x minus 1 with x minus 1 in the denominator. And so now I'm looking at limit as x approaches 1 of x plus 1. Limit of a sum is always the sum of the limits, right? But I can make a direct substitution. Since 1 is in the domain here, just directly substitute in that number and go to the answer now. 1 plus 1 is 2. Of course, remove the limit notation at that point. I'm no longer writing that down. And I'm getting 2 as the value of that limit. Now, 2 was the number that we had guessed based on using a table. Okay, so we had guessed correctly for that problem. Okay, I mentioned, be careful about guessing. Okay, I would not use tables at all. Okay, unless you're told to use a table. It's very easy to guess wrong. Of course, I'm going to want to see the work here for these problems. Let's do a few more limits where we have to manipulate the inside. Okay. So, for example, what if I want to find the limit as x approaches negative 3 of 3x squared plus 7x minus 6 over x plus 3? Well, I can't directly substitute in negative 3, right? That's a problem because I know I can't divide by 0. So, my limit law, saying that the limit of a quotient is the quotient of the limits, does not apply. You can only use this law provided the limit of the denominator is not 0. Okay, so I wouldn't want to use my limit law in this problem here, otherwise it's like I'm saying I'm dividing by 0. Okay, I'm going to have to manipulate the inside like I did on this other problem. The numerator factors nicely, and that's going to allow me to cancel an x plus 3 with an x plus 3 down under. Okay, and so now I'm looking at the limit as x approaches negative 3 of 3x minus 2. I can now directly substitute in negative 3 into the expression here. Remove the limit notation. 3 times negative 3 is negative 9, minus 2 is negative 11. So negative 11 would be my answer there. Okay, here's another one. The limit as h approaches 0 of 3 plus h squared minus 9 all over h. Well, I can't directly substitute in 0, right, because I know I can't divide by 0. So again, that my limit law, the limit of a quotient is the quotient of the limits, does not apply for this problem here. Well, let's go ahead and try to algebraically manipulate the inside in order to make it so that we can directly substitute in that number. In the numerator, I have FOILed out 3 plus h times 3 plus h to get 9 plus 6h plus h squared. 9 minus 9, those cancel. And so that's going to leave me with 6h plus h squared in the numerator, which, okay, I still can't directly substitute in 0 there. But if I were to factor out an h from these two terms, I can cancel that with the one in the denominator. Okay, so that's what I've done in the next step here, factored out an h and then canceled. And so now I'm looking at the limit as h approaches 0 of 6 plus h. Well, now there's no problem with directly substituting in 0, and so I'm going to do that. The answer is 6. Okay, here's another one. The limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. I can't directly plug in 0, right, because there's a problem with division by 0. So this would be another problem where I'd want to algebraically manipulate the inside. Okay. Now, for this problem, I'm going to rationalize the numerator. Rationalize the numerator is just fancy words for saying get rid of the radical that we currently see in the numerator. Okay, well, to do that, I'm going to multiply the top and the bottom by the conjugate of what I see in the numerator. Conjugate just simply means switch that sign that's in the middle to its opposite. Okay, so I'm going to multiply the top and the bottom by a square root of x plus 1 plus 1. The square root of x plus 1 over the square root of x plus 1, well, that's 1, right? So there's no harm in doing what I'm doing here. I'm not changing anything if I'm just multiplying this inside here by 1. Okay, like I'm changing the form, but I'm not changing the number. Okay. Check it out. Now, in the next line, if I FOIL the numerator, square root of x plus 1 times square root of x plus 1 is x plus 1. The reason for using the conjugate is because now the middle term is going to go to 0, and therefore we no longer have a radical in the numerator. That's what we want. Go to the last term now. Negative 1 times 1 is minus 1. Okay. And 1 minus 1 is 0. Those terms cancel. After you cancel those terms, x over x can be canceled, right? And so now I'm looking at the limit as x approaches 0 of 1 divided by the square root of x plus 1 plus 1. At this point, there's no problem with directly substituting 0 into the function, okay? I don't get 0 down under, so I've done that. Remove the limit notation. And 1 over 2, so 1/2 would be the answer to that problem. Okay, so the goal is to try to algebraically manipulate the function so that we can make a direct substitution, okay? Many times we won't be able to do that. That's what I was talking about up here, okay? In these problems we could. There was no, there's no problem with that. But most of the problems are going to be where you're going to have to use some algebra, manipulate the inside, and then try to make it so that you can get a direct substitution.